Good afternoon, everyone. I'm a PhD candidate from Xidian University, China, and Purdue University. Since the authors of this work cannot attend the conference in person, I'm here to present this work on behalf of the authors in Professor Xiaofeng Chen's group at Xidian University. The title is Pixel Plus and Pixel Plus Plus, compact and efficient forward circuit multi-signature schemes for POS blockchain consensus. Blockchains power diverse applications in the real world, with a strong focus on digital finance. A blockchain is a public distributed ledger. It consists of a series of blocks. These blocks are maintained by numerous nodes or miners in a peer-to-peer network. Blockchain's strengths come from consensus protocols used by many participants. Its core function is to handle block proposals and ensure nodes agree on the block sequence. In early blockchain methods, like Bitcoin, consensus is mainly achieved through proof of work, named POW for short. This requires all network nodes to solve a computational puzzle at the same time. However, POW is highly energy-intensive. Proof of stake, named POS for short, allows network nodes to vote on block proposals based on their stake. So it is less wasteful than POW and is one of the most attractive alternatives. Improving the efficiency of the underlying signature scheme becomes extremely important to the usability of POS consensus protocols, and this is where multi-signature comes in. In most POS consensus protocols, network nodes vote on block proposals by generating digital signatures, which are weighted by their stake. Consensus is reached when the number of signatures on the same block proposal hits a threshold. Because there are many blockchain nodes, this results in a large number of signatures being transmitted and stored over the blockchain network in each round of consensus. Therefore, improving the efficiency of the signature scheme is crucial for POS protocols. This is where multi-signature technique becomes important. Multi-signature is a cryptographic primitive that allows multiple signers to sign the same message, named the block proposal. These signatures are then aggregated into a single shorter signature, regardless of the number of network nodes. That means we can replace multiple signatures with a single one. This multi-signature can be verified as efficiently as a single signature. It significantly reduces both the time to check consensus and the storage needed for blocks. As a result, multi-signature is quite popular in POS blockchains. When we say blockchain provides an integrity guarantee, we usually assume that most nodes are not corrupted. In a POS blockchain, this means the fraction of corrupted signed keys must be below a certain threshold, such as 2/3. However, in practice, signed keys can be more easily corrupted than expected. For example, users with smaller stakers may not protect their accounts as well as active users. Also, users who sell their stakes may no longer return their signed keys. Once the fraction of corrupted signed keys exceeds the threshold, it will bring the problem of posterior corruption, also known as long-range attacks. In this scenario, an adversary can use corrupted keys to regenerate signatures for any block proposals at any point in the past. They can also modify the history and fork the blockchain. It can completely destroy the usability of the blockchain. Therefore, this is a major issue we want to address. The solution is multi-signature, which is forward circuit. This primitive divides the system lifecycle into discrete periods. It uses a key evolution mechanism to update the signed key at regular intervals in one direction. In each period, the signed key changes, but the public key stays the same. As a result, a corrupted signed key from period T cannot be used to forge signatures for periods before T. This achieves what is known as forward security. Pixel is the only available forward secure multi-signature scheme, was proposed as USENIX 2020. Their construction is based on a binary tree and uses a key structure hierarchical entity-based encryption, resulted in a logarithmic cost. For example, in a binary tree of deep 3, the initial signed key SK0 has 4 components, as colored in red. Its security relies on a non-standard Q-type complexity assumption over bilinear groups. Like other forward security primitives, its forward security is coarse-grained. This means that even if the signed key is corrupted, the adversary can still forge signatures during the current period. The above state-of-the-art method raises a key question for our work. Can we build forward secure multi-signature schemes with different performance and security trade-offs? We answer this question with a definite yes. Our first construction, Pixel Plus, is based on the RSA group. The global public parameters include an RSA modulus N, a generator G of the corresponding quadratic residuals group, and a group element U, which is computed as G to the power of the product of a series of prime EI. We use a hash function, H primes, to map an integer I into a prime EI with fixed length. The public key for a user is U to the power of S, where S is a random integer. We use the RSA sequencer to involve the secret key, which is crucial for achieving forward security. For the ith period, the actual signed key SKI is computed as the EI's root of the public key PK. At the end of this period, the signed key is updated by computing the EI plus ith root of the public key PK. To sign a message M, we first map M and the period T to an integer R, and map all signers' public key to another integer AT. Then we computed the signature sigma as the signed key SKT to the power of I times Q. All signatures can be aggregated by simply multiplying them together. During verification, the verifier needs to recompute the random integer I and check sigma prime to the power of EI equals APK to the power of I. Note that the aggregated public key APK is generated beforehand and is independent of the signed message M. The correctness of Pixel Plus appears to be straightforward. The security of Pixel Plus is proved under the standard RSA assumption and offers stronger security guarantees than non-standard assumptions. Pixel Plus does not use bilinear mapping, but contributes to its excellent performance. For a 3070-bit RSA modulus with 2 to the power of 32 periods, the signature consists of just one RSA group element, roughly 0.9 kilobytes. Sign takes 0.07 seconds, and verification takes 0.14 seconds, which make Pixel Plus notably faster than Pixel. Our second scheme is Pixel Plus Plus. It's a punctuable multi-signature scheme based on a symmetrical bilinear map. We use the BLS signature scheme as the base and use similar structures for public and signed keys. Specifically, we adopt the concept of punctual encryption and use a Bloom filter to manage the signed key. This means we create a BLS-style signed key SKI for each position I in the Bloom filter state. To sign a message, we first test the message on the current state of the Bloom filter and find an index L prime where the corresponding value is 0. If there is no such index, the sign fails. We then use the sign key component SKL prime to create the signature, similar to the original BLS signature. Due to the favorite property of the BLS signature, we can aggregate these signatures by multiplying them together. The verification process is also similar. The key evolution in Pixel++ is completely different and simple than in previous schemes. After signing a message, we add the message to the Bloom filter and remove the sign keys indexed by the hash values of the message. This ensures that the sign key cannot be used to sign the same message again, thereby achieving forward security. The most notable feature of the Pixel++ is that it revokes the sign capacity of individual messages, unlike Pixel and Pixel+, which revolve by periods. This means Pixel++ offers fine-grained forward security. In terms of performance, it has nearly the same sign and verification costs as Pixel, but its key evolution is 1,000 times faster. Our construction also has limitations. For Pixel+, it requires a trusted setup to generate the RSA modulars. This may aid the computation and communication costs, but we can address this issue by using a distributed method for circularly producing the RSA modulars. Many well-studied solutions are available for this. For Pixel++, although it achieves fine-grained forward security, there is still a chance of failing to sign due to the use of Bloom filter. Fortunately, we can adjust the Bloom filter parameters to minimize this failure probability, balancing usability and performance. This trade-off seems acceptable for POS blockchains. And thank you for your attention. To ensure your question can be answered correctly, if you are interested in any details about this work, please feel free to contact the authors through email. Thank you.